Hello students, today we are talking about Grignard reagents, one of my favorite classes of reagents. So Francois Grignard was a French chemist born in 1871 in France. At the suggestion of his mentor, his graduate professor, he pursued work with haloalkanes and magnesium, the reaction together with other carbonyl containing reagents. And eventually he went on to win the Nobel Prize in 1912, so I'd say that worked out pretty well for him. So here's an example of a synthesis of a Grignard reagent. So we are using a haloalkane, or an alkyl halide. This one has bromine. So in reaction with magnesium metal and diethyl ether will yield a Grignard reagent. So these are alkyl halides that we're using, so that means bromine, chlorine, or iodine. However, fluorine won't work very well. And this is what's considered a heterogeneous reaction. So that means it's using more than one state. So while all this is in solution, the actual reaction is happening on the magnesium, the solid surface. So that's why it's considered a heterogeneous reaction. This is all also occurring in diethyl ether, and that's very important. So we have a representation of the Grignard reagent, and the bond between the alkyl group, or alkyl or aryl group, bonded to the magnesium. This is a very polarized bond. So we have an uncommon occurrence, where carbon actually has a partial negative charge, with the metal having a partial positive charge. And so this is very polarized, not to mention the the magnesium and the bromide. These are an ionic pair. So all this is just very, very polar. And organic solvents tend to not dissolve very, very polar substances very well. But in this case, we're able to use diethyl ether or something else like tetrahydrofuran. So why is diethyl ether different? It's because it is able to coordinate with the magnesium in order to stabilize it. So right now, magnesium essentially has 4 pairs of electrons currently. So the electrons in the diethyl ether are able to coordinate and sort of donate their electrons to magnesium and stabilizing it, filling its octet, which is very, very stable. So this is sort of what drives the reaction. The reaction is trying to get to a very stable state. So now we have our Grignard reagents. Let's use them. So ketones and aldehydes. Here we have a representation of a ketone, or if you wanted, this R group could be a hydrogen, so it could be an aldehyde. So this again is polarized bond between the magnesium and the alkyl group. So this will be a nucleophilic addition reaction with the carbon in the alkyl group acting as the nucleophile onto the electrophilic carbon in the carbonyl carbon. So the oxygen and the carbon, they share bonds, or the double bond, but oxygen is more electronegative, so it's pulling the electron density more towards itself, so causing the carbon to have a partial positive charge, in which this will attack, breaking this double bond here and pushing 2 of the electrons onto the oxygen, forming our alkoxide. So usually after Grignard reagents, we'll add some sort of product workup. So we'll have protons for our alkoxide to grab to in an acid-base reaction, and we are forming our final alcohol product. So Grignard reagents, their products are alcohols. So with aldehydes, you can get secondary alcohols, though if you're using formaldehyde, then you'll end up with a primary alcohol, which is useful, but it's not something that is normally used. There's other ways of getting our primary alcohols using Grignards. With ketones, we'll form our tertiary alcohols, because with ketones we have 2 R groups to begin with, and then we're attaching one more with our Grignard reagents to get our tertiary alcohols. And now, something unique about this Grignard reagent is that it's forming carbon-carbon bonds. And for organic chemistry, this is synthesis. This is very important because you can always change the functional groups and have it react, but to actually form bonds between carbons is considered very, very useful. So, esters and acyl chlorides. So here we have similar setup with carbonyl, but then we have the difference is the leaving group. So this leaving group can be an ester, it can be your oxygen and an alkyl group, or it can just be chloride. Either way. But in a similar reaction, the alkyl group is nucleophilic and will attack the carbonyl carbon, pushing off the electrons, breaking this double bond, and forming our oxide. But instead of a product workup and creating the alcohol right off, this double bond will reform and pushing off the leaving group, with the leaving group grabbing the electrons between the bonds, and between it and the carbonyl carbon, and it is leaving, thus forming a ketone. Or if this was a hydrogen, then I guess we'd be forming an aldehyde. And with that, we're able to react one more molecule of the Grignard reagent to form our alcohol. So with esters and acyl chlorides, we're actually able to react 2 molecules of our Grignard reagent for every 1 molecule of our other reagent, of our carbonyl group. So here's just a side note that I was talking about earlier about the primary alcohols. A more useful way is to use oxocycloalkanes. So with this representation of a Grignard reagent, the carbon nucleophile will attack one, it doesn't really matter, one of these, will attack one of these carbons bound to the oxygen, which has a partial positive charge, and breaking the ring, putting these electrons onto the oxygen and forming an oxide. And again, with a short product workup, as we've shown before, we're able to get our primary alcohols. So using different heterocyclic alkanes or cycloalkanes, we're able to form different primary alcohols. And now with our experiment. So what we're using today is this benzophenone and our phenyl magnesium bromide. So with the alkyl group of the magnesium, this will act as the nucleophile onto the carbonyl carbon of the benzophenone, breaking the double bond just as we've shown before with the other ketone, and forming an alkoxide. And with our product workup, with our HCl, our aqueous HCl, we are forming our final product, which is the triphenylmethanol. And instead of today using the NMR, we're actually moving on to gas chromatography. So that'll be interesting. So I hope you guys enjoy the lab, and I'll see you there. Bye.